Hey there, students. So we are still working on being able to describe the organization of the modern periodic table. And we had mentioned in our last lesson that elements that fall in the same column together, the same up and down column, have similar electron configurations. And those similar electron configurations cause them to behave in similar ways. So they have similar properties. So those elements that fall into the columns together, we group them together into what we call families of elements. And so in our lesson today, let's talk about some of the different families of elements. The first family I want to talk about is hydrogen. Hydrogen is often grouped into a family just all by itself. Hydrogen is the simplest element. It's number 1 on the periodic table. It consists of just a proton and an electron. Hydrogen is often grouped into a family just by itself. Some things about hydrogen. Hydrogen is the most abundant element in the universe. More than 90% of all the atoms in the entire universe are hydrogen atoms. When you look out into space at like the stars and the nebulas that are out there, they are composed almost entirely of hydrogen. So hydrogen is a very common element throughout the universe. Hydrogen is an invisible gas. Hydrogen is explosive. And usually we understand hydrogen to be a nonmetal. But if you think back to a graphic that we saw in our lesson the other day that shows where the metals are located on the periodic table, you might recall that hydrogen is on the side of the periodic table where we find the metals. And kind of an interesting thing is that scientists think that under really extreme temperatures and pressures, hydrogen might change from a nonmetal to a metal. And that's never really been observed, but they think that inside the core of some of these really big gas giant planets like Jupiter and Saturn, the hydrogen inside of those planets towards the center where the pressures and the temperatures are extremely high, you might find metallic hydrogen. So there may be places in the universe where hydrogen actually is a metal. Also kind of interesting when you think about hydrogen having to do with astronomy. Hydrogen is a really important element for astronomers. Like I mentioned a minute ago, stars are composed almost entirely of hydrogen. And over a star's life cycle, in the core of the stars, what they do is they take hydrogen and they undergo a process called nuclear fusion, and they turn that hydrogen into helium. And as the star ages and the process continues, eventually they're able to take that helium and undergo nuclear fusion and produce larger and larger elements. And inside the cores of stars, they're able to produce elements as large as iron. Okay? And then when the star nears the end of its life cycle, it will, some of them will explode in a process called a supernova. And in that supernova explosion, atoms of different elements can fuse together and form even larger elements. So all of the atoms that exist that are not hydrogen atoms were created in stars. Somebody once said that you and me were made of star stuff, because all the atoms that make up our bodies, all the atoms that make up the things around us, were created in the cores of ancient stars. So it's kind of a neat, interesting thing to think about. Okay, underneath hydrogen on the periodic table, you find a family of elements called the alkali metals. The alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. They're called the alkali metals. The alkali metals have some properties in common. They are all soft metals. This might be a little bit strange when you think about a metal, is that these alkali metals are easy to cut. So you could easily cut a sample of one of them with something like a butter knife, right? You think about a metal, usually it's really, really hard to cut a metal, but these metals are very easy to cut through. They are easy to cut, they are shiny metals, and they're all very, very reactive. In fact, they will react with water. As you go down the column, they become even more reactive. So if you put some lithium in water, you'll see a reaction take place. But going down the column, if you put some rubidium in water, you better stand back because it's a pretty big reaction. And I'm gonna put a link to a video here where you can see each of the different alkali metals reacting with water. It's not my video, it's somebody else's video because I don't have samples of all these different alkali metals. But you can see them reacting with water, and it's kind of an interesting thing to watch. Alkali metals all have electron configurations that end with the S1. So, you know, lithium is 2s1 and sodium is 3s1 and so forth, right? They all end with a S1, and they all form ions that have a positive 1 charge. They're called alkali metals because when they react with water, they form alkaline solutions, right? It's kind of alkaline, it's kind of like the opposite of an acid, right? So they all react with water to form alkaline solutions, and that's the alkali metals. Okay, now I don't have samples of all the different alkali metals, but I do have some sodium. And I thought, you know, let's go ahead and let us react some sodium in the water and get that in the video, so that'll be nice. And you can see it is in this really old can. This must have been in the storeroom for 13 years, it says. Okay, inside the can I have sodium. Okay, and inside the bottle, this sodium should be stored under some oil. Yeah, there's some oil in there. I doubt you can see that very well. Let's see if I can snag a piece of this out. It's stored under oil because sodium will react not just with water, but it will react with the moisture in the air. And so when you look at this, see if I can grab a piece. Try not to get oil in my fingers. Okay, there we go. Let's see if you can see this. It doesn't look like a metal, right? It looks kind of weird. It looks kind of white, maybe like a nasty tooth or something, right? But that's just a little coating of what has been created when the sodium reacts with the moisture in the air. So I'm going to try to cut through this here. You see, I just cut through it with a plastic spatula. That's how soft it is. And you can look inside there, and there's actually very little sodium left in there. I don't know if you can see. You can see a little bit of metal left in there in the middle. Let's put this in the water and see what happens. Try to react it with the water here. I don't know if it's going to be very good because there's you can see some reaction going on there. There you go. Notice it started on fire. Better put the cap back on my sodium. So pretty neat. Should I have put on my lab equipment to do that? Yes, I should have, and I didn't. But you know, sometimes. Pretty neat, right? So I'm sure that you're aware that the alkali metals are found in the S block in group 1 in the first column, right? Also in the S block, sharing the S block with the alkali metals, in group 2, column number 2, you find the alkaline earth metals. And the alkaline earth metals include beryllium, magnesium, calcium, strontium, barium, and radium. And they are all shiny metals. They're silvery white in color. They're less reactive than the alkaline metals, but they're still quite reactive. They all have electron configurations that end with an S2. So beryllium is 2s2, and magnesium is 3s2, and so forth, right, as you go down the column, 2s2, 3s2, 4s2, and so forth. And they also, they all form similar ions as well. They form ions that have a charge of positive 2. And you should probably see a picture of the different alkali metals that I'll add while I'm editing this. Okay, a couple more things about the alkali metals, the alkaline earth metals. They all react with water to form alkaline solutions, which is why they're called alkaline earth metals, right? And they also react with oxygen in a 1-to-1 ratio. And back in the day, in olden times, these compounds with oxygen were called earths, so they're called alkaline earth metals. Okay, the next family I want to talk about is all the way over on the other side of the periodic table. In column 18, you find the noble gases. The noble gases, you got helium, neon, argon, krypton, xenon, and radon. Right? These are called the noble gases, all the way over in column number 18. The noble gases, pretty interesting. They are almost completely unreactive. So when we talked about the alkaline metals and the alkaline earth metals, they were both very reactive. The noble gases are almost completely unreactive, right? They form almost no compounds at all. And you can kind of tell why by looking at their electron configurations. Their electron configurations all end with a p6. So that last orbital is full, right? And I know we haven't talked about why, different elements form compounds and such yet, but, this is a big reason why the noble gases don't form compounds, because their last orbital is already full, right? And they don't form ions either. So we talked about the alkaline metals form positive 1 ions, the alkaline earth metals form positive 2 ions, the noble gases form no ions. Why are they called noble gases? I think the gases part is kind of obvious because they're all gases. But, I like to say, think about the word noble. What does the word noble mean? Somebody who's noble is kind of like, aristocratic, and they're like above everybody else, and they're not going to fraternize with the rest of the, little people and such. And that's kind of what the noble gases do, right? Because they don't form compounds. They don't, fraternize with the other elements. They just kind of be by themselves, better than everybody else, some kind of hoity-toity elements or something, right? And that's the noble gases. Okay, right next to the noble gases, in column 17, you find a family called the halogens. The halogens, you've got fluorine, chlorine, bromine, iodine, astatine. Notice they all end with ene. These are the ene elements, the halogens. The halogens are very reactive elements again, right? So in columns 1 and 2, the alkaline metals and the alkaline earth metals, they were very reactive. And now here, all the way on the other side, in column 17, you've got the halogens, which are also very reactive. The halogens form strong acids when they're combined with hydrogen. So if you take, chlorine and hydrogen, they form hydrochloric acid. Or if you take fluorine and hydrogen, you make hydrofluoric acid. And these are strong acids. All the halogens in column 17 have an electron configuration that ends with a p5, right? They're all p5. So fluorine is 2p5, chlorine is 3p5, and so forth down the column. And they all form ions with a charge of -1. So over on the other side of the table, with the alkaline metals and the alkaline earth metals, they form charges that were positive. The halogens form charges that are negative, -1 charges on the halogens. Okay. Halogens, the word halogen, it actually comes from Greek, and the word actually means literally salt maker, right? When they combine with a metallic atom, notice these are nonmetals on this side of the table. When they're combined with a metallic atom, they form compounds that are known as salts. And halo is Greek for salts, and gen for the word maker, so halogen, salt maker. Pretty neat, huh? Okay, those are the major families, right? Just a couple of other families here to talk about and mention real quick. Next to the halogens, in column 16, you have a group. Some people call it the oxygen group because oxygen's at the top of the group, but it does have a name. It's called the chalcogens, right? So if you don't remember the word chalcogen, that's okay. It's the oxygen group, or it's the chalcogens. And that includes, oxygen, sulfur, selenium in that column. They're called the chalcogens. All the chalcogens have an electron configuration that ends with a p4, and they form ions that have a -2 charge. So, the halogens have -1, the chalcogens have -2. Okay. And then the column next to the chalcogens, in column, what is it now, 15? Some people will call this the nitrogen group, but it does have another name. It's called the pnictogens. It starts with a P. I know it's a really weird word. It starts with a P, but a silent P. Pnictogens in column 15, including nitrogen, phosphorus, all the ones in that group, right? They all have an electron configuration that ends with a P3, and they form ions that have a -3 charge. So that group is called the pnictogens. And then let's be aware of a couple of other what you might consider families that we've talked about in previous videos. The transition metals, what we've called the D block, is also called the transition metals. They all have electron configurations that end with a D something, right? These ones, it's a lot less simple to predict what kind of ions they form. So the alkali metals, the alkaline earth metals, the noble gases, the halogens, the chalcogens, the pnictogens, just by knowing what family an element is in, I can tell what it's what kind of ion it's going to form, whether it's going to be +2 like the alkaline earth metals, or it's going to be -2 like the chalcogens. I can tell just by the column that it's in. But with the transition metals, you can't tell quite as easily what its charge is going to be, what the charge for its ions is going to be. Yeah, so those are the ones that are set down a little bit in what we've called the D block, the transition metals. Down below that, what we've called the F block, these are called the rare earth elements, or the rare earth metals, and they include all the ones down at the bottom, that are usually pulled out of the periodic table. And again, these ones aren't quite so straightforward to figure out what the charge of their ions is going to be, but all of their electron configurations end with an F something, right? F something, the rare earth elements. Now those rare earth elements that are in the top row of that are called the lanthanides, because the first one in that row is lanthanum, so that row is called the lanthanides. And in the bottom row there, it's called the actinides, because the first one is actinium, so the row is called the actinides. So those are pretty much your basic families of elements. So that was a little bit about the different families of elements: the alkali metals, the alkaline earth metals, the noble gases, the halogens, the chalcogens, the pnictogens, the transition metals, the rare earth metals, lanthanides, actinides, all that fun stuff. Hopefully that helps us describe the organization of the modern periodic table. And until next time, take it easy.